Everybody, so this is an interesting circular motion question from exercise 7D. This is question 10 from Fundamental Applied Maths. So the question starts, a particle of mass m is suspended by a light inextensible string AB of length 2d. So there I have my length 2d between A and B. The end A is fixed. Particles released from rest when AB makes this angle alpha with the downward vertical through A. When B has risen again to a height so that AB makes an angle of 45 degrees with the downward vertical, the midpoint of the string comes into contact with a small horizontal peg C. Okay, so we have this little variation here where we have this peg. If cos A is equal to a quarter, find in terms of D the speed of the particle at the moment that the string touches the peg. Okay, so when in these questions, when we have to consider different positions, we're gonna use conservation of energy quite often here. Okay, so what we're going to do is consider two positions here. The first one is our starting position B, and obviously the nice thing about our starting position B is that the particle is released from rest, so our speed is going to be 0 at B. And our second position that we're going to consider is this point down here, directly below A. This is going to be position 2. And the nice thing about that is that our height is going to be 0 at that point. So we'll call that 0. That's the very bottom of the motion. And that'll make things nice for our conservation of energy. Obviously, when we're looking at position B, we want to find what height B at position 1 is above position 2. So let's have a look here. It says first, let us find the height at 1. So if we're looking at the height of position 1, we can build a small triangle here. If I drop a horizontal line going from B to meet this vertical here, and I'll have this resulting triangle here. 2D is going to be my hypotenuse here. My angle alpha is up here. So this side here is going to be 2D cosine alpha. Cosine alpha is a quarter. So I get 2D for this length here. So then if we look at the whole triangle, the height at 1 is going to be this total height, 2D, minus this little section we found here, D over 2, which is going to give us 3 over 2. Right, once we found this height at position 1, we jump straight into our conservation of energy. So the two positions we're considering is the starting position, which I call position 1, and then the very bottom of our motion, which I'm calling position 2. So we have MGH, so we have our potential energy, which is our height 3D over 2, which I just found. Our kinetic energy, well, it's released from rest, so this is 0, is equal to our total energy at position 2. Of course, our potential energy is going to be 0, height is 0, and we have our kinetic energy here. So V is what we're trying to find. As is usually the case with these conservation of energy questions, all the M's cancel out straight away, which makes things quite nice. And then we find our velocity at position 2. Now, because I know that I'm going to have to use conservation of energy a few times and that it's always going to be V squared, I can save a bit of time here by just leaving this as V squared. I don't have to, put a square root on this side to find V. So this is our velocity at position 2. What can happen a lot of times in these questions is that we have V and H for a lot of different positions. So try and just be careful that you clearly mark out which V you mean, either by subscripting or just by literally writing in what you mean. So now let's consider positions 2 and 3. So they want us to find the velocity at this position 3 when the string makes an angle of 45 degrees with the vertical. So 2, same as before, it's the very bottom of the motion, and 3 is when we make this angle of 45. So again, we're going to have to find the height of position 3, right? The height of position 2, we know, 0. The height of position 3, well, we go back, we do a little bit of trigonometry again. So if I drop a horizontal over here, right down horizontal so it meets the vertical, I can see that I have this little right angle triangle to consider. And I can see then that the height I want to take away is going to be 2D cos 45. So the total length here is going to be 2D, and then the little section here is going to be 2D cos 45. Cos 45 is going to be 1 over root 2. So the height of this, the position 3 is going to be 2D minus root 2D. D for that one. Okay, we go straight into our conservation of energy again. And this time we're looking at positions 2 and 3. So again, at position 2, our height is going to be 0, quite nice. And at position 3, we're going to find a velocity, which is what the question wants. So position 2, 0 for potential energy. Our half mv squared, our kinetic energy for position 2. This is what we found just before, this root, this 3gg up here. So we're substituting that in. And on our right-hand side at position 3, well, our height, that's what we just found up here, 2d minus root 2d. And then our velocity squared, well, we don't know what the velocity squared is. That's what we're trying to find. M's cancel out straight away. We have M's in every term. And we're pretty much at our answer here when we get to this line. We just have to do a bit of messing around to get to our answer. Not too hard. Group everything on the left-hand side. It doesn't involve v squared. We eventually end up with this nice little formula here. And then when we put in 9.8 for g and take a square root, we end up with this. Expression for v in terms of d. Of course, we don't know d, so this still depends on d. But that's our velocity for part 1. Let's have a look at part 2. Part 2 is quite interesting because it says that the string comes into contact with this peg at point C, and then it's going to wrap around the peg. So the string wraps around the peg, and it wants us to find in terms of m the tension in the string when the particle reaches the same height as the peg. So it's going to make a horizontal here. It's going to be the exact same height as the peg. Okay, interesting one here. So yeah, in terms of the style of the question, we've already utilized conservation of energy quite a few times. So we're going to use conservation of energy again, and then we're going to have to look at how to bring in the tension of the string. And when we're going to bring in the tension of the string, we're going to be thinking of centripetal force. That's how we're going to bring in this. So here I've drawn out what this new circle is going to look like. So remember now, this is our original point A, the original point of our highest circle of radius 2d. But now we're wrapping around this middle peg at C, and we're going to have this smaller radius d. Position 3 is the same as position 3 before, so that's when it's making an angle of 45 degrees with the vertical from our original circle. And position 4 is going to be when our string is in a horizontal position. So that's our kind of our final position. That's where it's asking us, well, that's when it tells us that the string is going to rise up to here at the same height as the peg. So we can see here actually, there's once we know this initial triangle here, this initial angle of 45 degrees, we can see that you can also determine all these other little angles of 45 degrees here, which makes things very nice when we're looking at finding the height of position 4. So what our particle is going to be at position 4. Now there's a little trick here that makes our life a lot easier. When we were considering the conservation of energy in the first part of the question, we were doing all of our heights relative to the very bottom of the circle. So the very bottom of the circle here, so this vertical is 2d, and we had a height of 0 here at the bottom. Now we could keep doing that. We could keep doing that, consider the very bottom of the circle, you know, the bottom, and work out our heights relative to that. But it actually makes our life a lot easier if we use a little trick here and say that position 3 is now going to be the bottom, the starting position. And then we're going to say that position 4 is going to be a height relative to position 3. So that's kind of a useful thing to keep in mind for these conservation of energy questions. If we can kind of change our viewpoint to be a height relative to a different point where you can introduce a 0 for the height for one of the positions, then it's usually a good idea to do so. So in our case here, if we're looking at the height of 4 above 3, we're going to have this triangle here that we're considering. And to find the length of this red dotted line here, we can see that I can use d cos 45. I can use d sine 45, so it doesn't really matter, but d cos 45. It's quite nice. So this red line is going to have a height of d over root 2. And I'm not going to take that away from anything or anything like that, because I'm going to say that position 3 is 0, and then position 4 is going to be d over root 2, which will make my conservation of energy a lot nicer. So I'm looking at position 3, position 4. Of course, I have 0 for my height, because that's what I'm now considering to be my starting position. I'm going to have a half, for my kinetic energy, I'm going to have half GD 2 root 2 minus 1. And you'll notice here, I could have put in my value that I found exactly for V from part 1, but it actually makes my life easier if I just use this value here, this second last line of part 1 for V squared. Put that in for my V squared at position 3. And now position 4, well, I have my new height, D over root 2, that I just found here. And then I have my V squared over here that I do not know yet, but I will find at the very end. As always, M's cancel out. And I find the nice expression for V squared, which is my velocity, my speed at position 4. Now, here's an interesting thing to think about. We want to consider the forces at play at position 4. Okay, so when we're at this horizontal position at position 4, we want to think about the centripetal force and the tension in the string. First thing we can note is that the weight at this position is perpendicular to the string. Okay, so when we have our string here going horizontally, the weight is going to be acting vertically down. And that's only going to be the case when the string is horizontal. When the string is horizontal, the I component of the weight is going to be 0. And we can see that like this wouldn't be the case if we had any other kind of angle. Like consider here, like if I had a force at an angle here, well then when I think about my weight, when I think about mass times gravity, I'm going to have to take components of my weight, and there's going to be a component to this that I'm going to have to think about when I use my centripetal force formula. But at this exact moment when the weight is perpendicular to the string, I don't have to consider this. So we have here weight, force centripetal is equal to mv squared over r. So that's our formula for centripetal force. The full tension here of the string then is going to be our force, is going to be mv squared over r. Now our radius for this small circle is d. So the velocity that we've already found is this thing here. Plug those in for v squared. Sorry, that was our v squared value. Plug this in for d. And we get our value here. Now this is in terms of m, so we don't have the mass, but that's okay. So the tension in our string is 4.06 times the mass, newtons. Thanks for watching.